So the next talk is about climate change. And when I read this, I asked myself, so why do we need to know about this? So we are computer hackers. You know, it's always cozy and warm next to a big mainframe. We don't go outside. So what about the climate? But then I read something that each Google query produces 8.6 gram of CO2 of carbon dioxide. 20 Google queries would make for a kilometer with a modern car. So somehow we're connected with the climate, with the atmosphere. And lately there were lots of information, disinformation about global warming and the great global warming swindle I read somewhere. And now we have the opportunity to listen to Stefan Rahmstorf to get some first-hand information of the global climate research. And Stefan Rahmstorf is member of the I have to spell it right. Intergovernmental Panel on Climate Change. So some of you might have heard about this, and there's a very famous report. He was one of the head authors of that, and I'm looking forward to have a very, very interesting talk right now. So please give a warm welcome to Stefan Rahmstorf.
Yeah, thank you very much. I'm working at the Potsdam Institute for Climate Impact Research. I might add to this nice introduction. Thanks, by the way. Potsdam is just outside Berlin, as hopefully most of you will know, about 30 kilometers from here. And I'm not really a member of the Intergovernmental Panel on Climate Change. I'm just one of the scientists who has contributed to the last report, because this, the IPCC doesn't have real members as such. It has a small head office in Geneva, but mostly it's a voluntary initiative where thousands of scientists around the world contribute in one form or another to these reports. Just that as a point of clarification. My job today is to try and give you a current overview about what we know about climate change. And I will start with the very basic fact that the climate of our planet, at least as far as the global temperature is concerned, is a result of a very simple energy balance, and that actually applies to any planet. So with this you can calculate the average temperature of all the planets in the solar system. You might have recognized the sun on the top left there, and the energy that comes from the sun is of course what drives the whole climate system. And then a part of it, about 30%, gets reflected back into space, mostly by the bright surfaces, that is the cloud surfaces or snow and ice surfaces. And the Earth itself radiates energy in the long wave band like any physical body. It's called the back radiation or infrared radiation. And the global mean temperature simply adjusts so that this equation that you see at the bottom left there is satisfied. Namely, we radiate as much energy back out into space as we absorb from the sun. And this is an equilibrium, of course, but it holds to a very good accuracy. We can't be out of equilibrium for any substantial time. So that also means that there is only very few ways to change the global mean temperature. Either you have to change the incoming solar radiation, or you have to change the second term here, the reflectivity of the Earth, that's called the albedo. Or the third way is to change the outgoing long-wave radiation, and that's what you can do, for example, by changing the composition of the atmosphere, the amount of greenhouse gases in the atmosphere, because the atmosphere is not transparent for long-wave radiation because it contains gases like water vapor, carbon dioxide, and some others that are called greenhouse gases, and that interfere with this back radiation into space. So there are many things about climate that are very complicated, but this is actually something that's very simple, the energy budget that determines the global mean temperature. That's why we understand global mean temperature much better than any other aspect of climate, like regional temperatures or precipitation and so on. But I will talk about those as well. But I will start just talking about global temperatures. I will also start by taking a look back in time. This is the last 400,000 years. Sorry that the labels here are so small. I have a version of this with bigger labels, and I overlooked that I got the wrong version here. But anyway, this shows 400,000 years of climate change, and the blue curve is the up and down of the carbon dioxide concentration in the atmosphere as measured from ice cores from Antarctica, and the red curve here is the temperature in Antarctica from those ice cores. Many of you will probably recognize this because this is the point where Al Gore in his movie climbs on a ladder and he makes a slight mistake there. We have criticized that on our weblog, Real Climate. Otherwise it's a pretty good movie, but this story he doesn't get quite right. So what I want to tell you about this data is mainly two things. The first of them is that the CO2 concentration has varied between 190 and 290 parts per million for at least the past 400,000 years, as we see on this graph, but we now have a newer ice core, a European drilled ice core, the Epica core, which takes that back about 800,000 years, and it just continues on basically in the same way. CO2 nicely stays within those bounds of 190 and 290 parts per million. And that brings into perspective what has happened recently in the last 150 years or so, namely this increase of the carbon dioxide concentration to, by now, more than 380 parts per million, so it's an increase by about 1/3. And you have to go back several million years in climate history until you come to past climates where CO2 concentration was as high as it is today. And at those times, temperatures were also much higher than they are today. Oops. Can we get rid of this sound, perhaps? Is that possible? Oops. So or do I have to stand somewhere else to avoid this? Well, don't know. The second reason why I show this is because we use these past temperature variations to test the models that we have that we use to simulate climate on Earth. So what we see here is basically 4 glacial cycles. This is the first one, the second one, the third one, and the fourth one. And these glacial cycles are driven by changes in the Earth orbit. That's why I have this little schematic diagram up here, which shows those orbital changes. And these drive the ice ages. I hope that everyone knows that. I learned that in school in the early 70s, because this has been known since the 1920s, basically, the orbital theory of the ice ages, and it's been well confirmed since about the 1950s. And we can use this now to drive our climate models, first of all with these orbital cycles, which are known to great precision. You can calculate this from astronomy, basically. And the second thing we use is this variation in carbon dioxide concentration, which we know from the ice cores. And if we drive a climate model with these two driving forces, these two forcings as we call them, then we can simulate past climate variations. And this movie shows you the last 200,000 years of climate. Time is running at the bottom here. We're about 150,000 years before present now at this point. And what you see here is the big ice sheets covering the northern hemisphere. Now they're vanishing. Only Greenland is ice covered. That was the Eemian interglacial. And we're now gradually moving into the next ice age. Again, that's the last ice age that reached its maximum extent about 20,000 years before present. And now we're about 40,000 before present, so you can see we're gradually approaching this maximum extent that was just there now, and then the ice relatively rapidly vanished again into the Holocene, which is the warm interglacial that we live in today and that we have lived in for the past 10,000 years. That was a time when humans invented agriculture and developed their civilization. The reason why I show this is, first of all, because I think it puts the current climate changes into a longer term perspective, and secondly, I think it's a nice success that we can model these things now with our climate models, the same model that we also use to do projections of the future, or other times in the Earth history we simulate with the same climate model. Let's get closer to the present now, though. This is the last 10,000 years, and again I show you the CO2 concentration, so it's just a part of the same thing that I showed earlier. This is the Holocene, pretty stable carbon dioxide concentration around about 280 parts per million, and then here you very clearly see that strong increase that has happened since. And we know for sure that this increase in carbon dioxide concentration has been caused by us, by human activities. The reason why we know that are manifold, but the most simple reason is that we simply know how much we have emitted. We know how much coal, oil and gas we have dug out of the earth and burnt, and CO2 is simply the main combustion product, so we know how much CO2 we have emitted, and this rise that we observe in the atmosphere is actually only about half of what we have emitted. So there is no question that perhaps this CO2 might have come out of the natural Earth system. To the contrary, we know the natural Earth system has taken up CO2, about half of what we have emitted. There are other reasons why we know this rise is caused by humans. One more technical reason is that the isotope composition of fossil carbon is different from the carbon that naturally cycles in the ocean, in the biosphere and in the atmosphere, and that was already shown in the 1950s that this rise is due to fossil carbon because of its isotope composition. I just said that about half of the CO2 that we put into the atmosphere is not there anymore. It's gone. So where is it? Most of that is in the ocean. The oceans have also increased in CO2 concentration. That is proven by shipboard measurements. And this is a problem in itself because carbon dioxide in the ocean forms carbonic acid, and that makes the ocean more acidic. And that's a problem because it interferes with all the organisms in the sea that form calcium carbonate shells, like this microplankton that you see here, or the coral reefs. They are all made of calcium carbonate, and you can only do that if you have enough calcium carbonate in the seawater, if it's supersaturated. And by adding more CO2 you shift the chemical balance so that you get into a state of undersaturated calcium carbonate. We'll get there in about 50 years if we don't stop the rise in CO2 concentration and CO2 emissions, and then we will see major impacts on marine life. For example, colleagues in Bremerhaven have grown this microplankton in seawater enriched with carbon dioxide, and you see that you then get very malformed shells, etc. It's just not viable anymore to form these shells. It's the same as the seashells that you find on the beach. You can't do that if the ocean water becomes too acidic, and then these organisms are at the basis of the food chains in the ocean. So we are really playing with the entire ocean ecosystem here in a major way. To me, as an ocean scientist, this would be alone enough reason to stop increasing the CO2 concentration in the atmosphere, even if CO2 didn't cause climate change. But we know that apart from ocean acidification, it does also cause climate change. because carbon dioxide is a greenhouse gas which interferes with the long-wave radiation that is radiated from the Earth into space. And that is not terribly new. That's been known since the 19th century, actually since the early 19th century, but the effect was first quantified in the late 19th century in this famous paper by the Swedish Nobel Prize winner Svante Arrhenius, who calculated the effect of a doubling of CO2 concentration in the atmosphere in the year 1896, and his result was that you get a global warming of 4 to 6 degrees centigrade if you double the CO2 concentration.